to finish this, and then what I suggest is that I go directly onto the paper, which allows us to finish in good time so that we can all enjoy the afternoon. Right, because this slot, although I say we've got this 4 hours, and we do need these 4 hours available when we're doing some practical work, is not really possible to sensibly carry on doing lectures for 4 hours.
Good.
Entirely agree. His hearing's not, his eyesight might be going, but his hearing's okay. I've totally forgot what I was going to say. Oh yes, next week, on Tuesday, this slot, on Tuesday, Kate and I will be running for a 2-hour slot only for the practical exercise. We want to go through with you to see what excellent progress you've made. So we actually will need you with your stuff, with a laptop, so that we can discuss with you what you've found so far and go through some results with you, so that we can actually do a more interactive session. So that's next week. Right, where are we? What we need to do is to look at one further aspect of how oceans move, the Ekman transport, and then we're going to look at a few currents and deep water formation and a few sort of other little odds and sods, and then we'll get on to the Agulhas current. The Ekman transport, actually we talk about Ekman transport with atmospheric circulation, but it originated, its first identification was in the oceans, where icebergs moved in a direction inclined away from the direction of wind by 45 degrees, which is a bit odd. That you could see the wind going in this direction and the iceberg travelling off in a different direction, which as you can see is slightly complication. In theory, the net deflection is exactly the same as we get in the atmosphere at about 90 degrees. So it's a drag on this, so we have this geostrophic balance, the pressure gradient, the Coriolis. We know we've got this sort of balanced geostrophic effect. But then the drag on the fluid, just as we get the drag on air, the fluid slows down, and the magnitude of the Coriolis, slows down the effect of the Coriolis effect on the changes. So if we actually look at it, it's exactly the same as we had in the atmosphere. There's this Ekman spiral, the wind's going in that direction, it's balanced, the pressure gradient is balanced against the Coriolis, and the net average movement is at a direction for this, and we get this spiraling effect that it's most at the surface and reduces as you get down with depth. And so the upper part of the ocean is affected by, especially as it gets close to land, by frictional drag on the ocean. And I won't go into this in detail because you can run this if you look it up, but you can actually work out if you, on this little thing where you go into this site. I won't try and get back into the internet for that. It'll only tell me that I can't do it. There's a very strong email going off to certain people about that. But effectively, if you go into this and you feed in data at different latitudes where the Coriolis force has a different effect, you can demonstrate the difference between the directions of Ekman transport and where most transport is going on. That explains it. So rather than go through it in great detail here, what I'd like you to do is to go into that site. I haven't checked it this year, it was working last year, and just get an idea of how it actually operates, and depending on how close you are to the surface, to the equator, and whether you're in the northern and the southern hemisphere. But the effect of this is that when you get these close to the coast, there is the drag effect of the coast starts to operate, and you can see how you can have wind, you've got water upwelling here, wind is coming in this direction, the Earth's rotating that way, and the net effect of the flow is to move water in this direction. So, and the same is true west coast, southern hemisphere, with a different wind, you move it from the, you get flow actually in. So in other words, the flowing of the surface current is not following the direction of the wind. It's basically Ekman transport, 45 degrees to that, and it's all due to this frictional drag on the water column. And it's most noticeable as you get close to continents. As you go out into the deep ocean, it's only in the very uppermost bit that you begin to get any effect of Ekman transport. Probably more important than that, as a concept which has driven a lot of our understanding about ocean circulation, is the idea of deep water formation. This idea that water circulation in the oceans is driven not particularly by wind or atmospheric circulation, but by the idea that there's a three-dimensional conveyor of water, which is driven by the ability of water to sink. And then, if you imagine water sinks, pulls in water behind it, and that generates up big currents, global currents. So, how does deep water form? Deep water masses have different properties from the surface. The different properties from the surface, here's a surface one, relatively high temperature, but variable density, variable salinity, low temperature, but quite reasonable salinity values. What happens? Denser water sinks. So the denser the water is, it will sink. And density increases as salinity increases and temperature decreases. So where you've got very cold, very salty water, it sinks. So at high latitudes, the net effect at high latitudes of the cold and if you've got high salinity, is that the water will tend to sink down to the bottom of the ocean, the water column. Now, this is enhanced by this process of brine exclusion. Seawater freezes and brine collects throughout small pockets in the ice matrix, which is water and salt. Brine is salty water, okay? So you've got big ice, water is freezing up, it's getting cold, and it's got a sort of brittly surface to it, brittly structure to it. It's got small pockets which has got quite a lot of this very dense or very salt-rich water, this brine. Effectively, that brine, because of its the concentration of the salinity, actually melts the ice directly below it and travels down through the ice. So effectively, as it freezes, the brine is expelled down through the ice column, melting the ice around it. This means that at the bottom of the ice pack, the water is very cold but has very high salt. So the net effect of freezing the surface of the ocean at high latitudes is to start this process of brine exclusion. And what happens is that as this freezes, this water with very high salinity, very cold, is concentrated at the bottom, and then effectively it's expelled from the base of the ice. As it's expelled from the base of the ice, it is much more dense than the surrounding water into which it's being expelled, so it sinks. So that water gradually sinks to the base of the ocean column. And that is deep water. And the two places where we get deep water formation in significant global amounts are the Arctic and the North Atlantic deep water, and the Antarctic, where you get Antarctic deep water. What would be the effect of producing an ice-free Arctic on global circulation then? You wouldn't have deep water formation. If deep water formation drives the system, then effectively you're going to change the whole conveyor belt of the global ocean system. In theory. Theoretically, if deep water formation drives the Earth's main ocean circulation, then if you cut off, especially the northern hemisphere, the formation of that deep water, you're going to get water not sinking and staying at the surface. And you're not, therefore, going to drive the movement of water around the Earth system. At the moment, this is the sort of idea that we've got, is that at the equator, here's our cells, heat being transferred away from the equator in the surface into gyres, In the Arctic, water that does get up to the Arctic as surface, so Gulf Stream comes up here, sinks right along here, produces NADW, which then flows out as a bottom current back towards the equator. In the southern hemisphere, exactly the same. Antarctic bottom water forms and flows back towards the equator. And it's very difficult to track exactly what happens to this water as it moves down. But we can see this element quite clearly being produced both at the high latitudes. And this has been described as the global conveyor belt, the thermohaline circulation. I've done this briefly with you before. And it is believed, or it has been believed for many years, that this is the underlying structure, the underlying thing that drives ocean circulation. So basically, this is the sort of diagram you will see. North Atlantic deep water being formed somewhere, especially off southern Iceland, a little bit in the Greenland, Iceland, Norwegian Sea, but especially here. Sinking, and not just then going back up here, but actually travelling right out from here and getting into the Antarctic and possibly into the Southern Ocean. How would we know that water here came from here?
Salinity and temperature, right?
Because the salinity and temperature should give us a density which is identifiable as that. It hasn't changed because it's travelling as a water mass. So the salinity won't change. The overall density won't change. Same is true here. Antarctic bottom water is forming and then going out into the circumantarctic current and travelling around and eventually probably joining up with the Atlantic water, going into the Indian Ocean, into the Pacific, and then becoming part of upwelling currents, especially where you've got upwelling taking place off Peru,